Hello there, Year 9 and 10. Welcome back to the fourth online physics lesson from St Leonard's Academy. I'm Mr Devlin, your host for this lesson. So last lesson we looked at key skills. And this lesson we're going to stay on key skills. We're going to look at, so last lesson we were looking at standard form and units. This lesson, we're going to look at unit prefixes, unit conversion, and significant figures. Now, it's going to be a bit of a mathsy lesson again, like last week's. And for that, I make absolutely no apology because these, just like last week, these are really, really fundamental skills for physics and for the rest of your life. So we've just got to get to grips with them, and there's no two ways about it. So, once again, I think this lesson should take us about an hour. You're going to need a pen, a piece of paper or two. Ideally, if you have a scientific calculator, that would be best because that's what you'll have in the exam, in your GCSE. It's best to get used to using one now as opposed to something else. If you don't have one, you can, however, use the calculator on your smartphone. Ideally, as well, if you have a quiet and clear workspace, that will help you to get the most out of the lesson so you're not disrupted. I can recommend as well putting your phone onto silent or even onto airplane mode so that you don't get calls or anything distracting you whilst you're doing the lesson. I've put mine on silent for this lesson so I don't get a call. Okay, let's move on. It's just chosen to freeze a little bit there. It's very helpful. Come on. There we go. So we've seen this last week and the week before as well. So I'm going to go very quickly. These are the work expectations from the St Leonard's Academy Science Department during the COVID lockdown. So we know that it's very difficult for students working from home, but we would like you to try to complete 3 hours of science work per week. That can be either the revision booklets that we sent home with you, the online lessons such as this one. So there's a physics, biology and a chemistry one come out each week. So if you do those 3 lessons, then that will be your 3 hours for the week. Don't forget to do the exit ticket at the end and submit it on shobi.com to get some feedback for your work. You can also do your own work, for example, revision using BBC Bitesize or Oak National Academy, or any other resource that you find. Okay, let's get stuck in. So, what can we see here? We've got our starter activity, we've got true, false. Before you have a look at that, have a look at these GIFs here. We've got the sun and the earth. These are not to scale. Note, what do I mean by to scale? The sun is in actual fact much, much, much bigger than the earth. Here they look like they're about the same size, but I assure you they're not. How much bigger or how much smaller are they? Have a look. Here we've got some facts about the sun, some facts about the earth. You can see that I've written these numbers in standard form. If you haven't done last week's lesson, then this won't make very much sense. And I encourage you, in fact, you have to go and do last week's lesson before trying this one. Otherwise, it's not going to make any sense. Okay? So you can see the mass of the sun is 2 × 10⁻30 kilograms. Quite a large number. The radius, the distance from the center of the sun to the surface, is 7 × 10⁸ meters. And the main elements by mass are hydrogen and helium. Earth facts, you've got its mass, 6 × 10⁻24. You've got its radius, 6.4 × 10⁶ meters, and its main elements as well by mass. Okay, so you've got true or false questions for the starter to do with orders of magnitude and standard form, the things we were looking at last week. For these, if it's about 100 times or 1,000 times or so on, to help you out, look at the order of magnitude of the standard form number. So, for example, for mass. If something is 100 times, approximately 100 times greater than, for example, 2 times 10 to the 30, then you'd expect the order of magnitude, the number that the power of 10 is raised to be 2 higher. So it would be 2 times 10 to the 32 would be something 100 times bigger. Anyway, that's a hint. When you pause the video, give them a go, and we'll go through the answers right afterwards. If you're a triple or a higher student, have a go at the extension task as well. Okay, you can pause the video now. Okay, I'm going to hope that you did pause it and give it a go. If you didn't give it a go, you're only sabotaging your own learning. Okay, so the Earth's radius is 6,400,000 meters. Have a look at the radius. We've got 6.4 times 10 to the 6 meters. If you multiply that together to get the normal number behind the standard form number, you will get 6,400,000 meters. That one's correct. The sun is mostly metal. Let's have a look at the main elements by mass, hydrogen and helium. That is false. Hydrogen and helium are non-metals. The sun, they're gases at this temperature. The sun is about 100 times the mass of the Earth. Let's have a look. Number 3. The mass of the sun is 2 times 10 to the 30 kilograms. The mass of the Earth is 6 times 10 to the 24. If you multiply those two out and divide 6 times 10 to the 24 by, divide 2 times 10 to the 30 by 6 times 10 to the 24, you will get about a million. Okay, the sun is about 1 million times more massive than the Earth. How about the radius? Number 4, the sun is about 100 times the radius of the Earth. We have, if you multiply these out and divide the larger one by the smaller one, you will get approximately an answer of about 100 times. It's not exact, but it is approximate. The sun is about 100 times the radius of the Earth. Number 5, the sun is powered by nuclear reactions. That is true. It's powered by fusion reactions of hydrogen and nuclei being fused, being pushed together and fused to form helium nuclei, nuclear fusion. And for extension, have a look at the answers I've just given. Here we go. There are the answers, if you didn't get them as I was going through. You can pause the video and write down the correct answer if you didn't have it. Okay, let's move on. So, that was going over some of the things that we did last lesson, and just to show you some of these huge numbers that scientists have to deal with day in, day out, which means we have to think of different ways of displaying numbers so that they make more sense to us. Standard form is one way. We're going to learn about another way to display very large or very small numbers. Okay, and just in case it wasn't clear from the numbers, we are a visual, we work much better with pictures and visual stimuli than numbers. That is a diagram of the Earth and Sun to scale. You can see we think of the Earth as being quite large. We are very small compared to the Sun. A huge burning ball of hydrogen and helium. Okay, so how about some other ways of writing large and small numbers? Imagine you asked someone how far it was to London from here, from Hastings. Which of the following would you rather hear? 114,000 meters, 1.14 times 10 to the 5 meters, or 114 kilometres? I know which one I'd rather hear, which one makes most sense to me, and that is 114 kilometres. Our brains, human brains, aren't very good at thinking of or understanding very large numbers. Numbers above about 1,000 actually don't make a huge amount of sense to us. It's much easier for us to think about them if we can convert very large numbers into different units so that they appear smaller. So the example for this would be 114,000 meters written in kilometres, converted into kilometres, is 114 kilometres. Okay. Another little example. Let's say you go to a bike shop, because I go to the bike shop because a screw has come off one of my bike's brakes and the brakes aren't working very well. I show the bike to the mechanic and I ask, what size of screw am I going to need to fix the brakes? The mechanic takes a look and they say 0.03 meters. You need a 0.003 meter screw. Now that might be correct, but I'm going to struggle to picture in my head how big that screw is, okay? Because 0.003, or you could also say it's 3,000th of a meter, is difficult for me to understand or to picture in my head. I've got a good idea about how big a meter is, yeah? But to think of 1,000th of a meter, it's difficult. It'd make a lot more sense if the mechanic was to say 3 millimeters, you need a 3 millimeter diameter screw. Now I've got a picture in my head of how big 1 millimeter is pretty well. It's very small, and 3 of them is very easy for me to think of. Okay, so I've converted from my SI base unit of meters to a different unit, millimeters, which makes more sense because I'm looking at things which are a bit smaller. And then the numbers I'm looking at are smaller numbers, which makes more sense to me. Numbers ideally between 0 and 100, but certainly, if possible, between 0 and 1,000. Okay, this system that scientists have invented for these numbers, we call them unit prefixes. The kilo for the kilometre, or the milli for the millimetre. As it says, scientists have developed a standard set of abbreviations to cut down the numbers that we need to write or say, and we call these unit prefixes. You probably haven't seen the term prefix too often or before. Looks not very nice, but it simply means a prefix is a word which goes before another word. So a unit prefix is a word which goes before a unit. As an example, 1,000 meters is a kilometre. The kilo is the unit prefix. Meter is the unit. Kilo is the unit prefix, which goes in front of meter. 1,000 meters is a kilometre. So instead of writing 1,000 meters, small m, I can write 1 kilometre, which for example, distances from between towns in the UK is going to make a lot more sense to me. The furthest distance from here to the furthest tip of Scotland is going to be about 800 kilometres. So those, by changing distances into kilometres, I can make units make a lot more sense than if I were to do it in metres. Unfortunately, there's no two ways about it. There's quite a few unit prefixes that we have to learn for our GCSE. And I've put a slash there for life, because you will see many of these in daily life. The large unit prefixes, so if you see no prefixes, it would be our base unit. If we go bigger than the unit prefix, we go kilo, mega, giga. You may... Sorry, video just cut out there. You might see a little blip. Yeah, if you you may well have come across kilo, mega, and giga if you have had anything to do with computers and computer memory. So computer memory is measured in bytes. The unit is bytes, and a kilobyte is a small unit, is 1,000 times the size of a byte. A megabyte is 1,000,000 times the size of a kilobyte of a byte, and a gigabyte is 1,000,000,000,000 times the size of a megabyte. So, for example, a good quality picture from a smartphone or an SLR would be might be 2 to 10 megabytes in size. But a small picture with a lower resolution, good for web use, might be just a few hundred kilobytes. You have most certainly come across kilo from kilometres. Kilo, you see the symbol K, stands for 1,000, so 1 kilometre is 1,000 metres. You've seen centimetres, so 1 centimetre is 1/100th of a metre. Millimetre is 1,000th of a metre. Now we've seen we're using meters there, but we could also use any other unit. So you could have a millinewton would be 1,000th of a newton. 10 millinewtons would be 10 times 1,000th of a newton. So we do have to learn these, and we have to learn the prefixes and the symbols, the meanings and standard form. If we had a lesson, in class, then I would hand you out a printed copy of this table for us to use for the next section. So the good news is the bad news is we have to learn it. The good news is most of this should go into your brain by osmosis by just using the table. But you need the table in front of you. So what I'm going to ask is that you copy down the table onto your paper. It doesn't have to be neat, because I'm not watching really, but you do need to get the information down. So what is the unit prefix? Please do it in order. Giga, mega, kilo, no prefix, centi, milli, micro, nano. What is the symbol? This is very important because often you'll only see the symbol. What does the symbol mean? What does the symbol or the prefix mean? And what is that number in standard form? That will help you with calculations later if you write down the standard form column. So giga, mega, kilo, no prefix, centi, milli, micro, nano. Now we need to know those, and we need to know them in order. It's difficult for us to hold so many strange, weird Latin and Greek words in our heads at one time. So it can help us to make a mnemonic, which is a kind of nonsense sentence which helps us to remember. I'm going to give you one mnemonic, which is, let's have a look. Come on. Great medieval killer centipedes make messes of ninjas. You might well think that mnemonic is stupid, and you may well think that you can do better. I hope that you can. Indeed, that's going to be one of the questions for the exit ticket. Note one more thing for this. So you need to write it down, copy down the whole table. One thing to note for the symbols, the case, whether it's capital or lowercase, is very important. You see a capital M stands for mega, a small m stands for milli. So you need to pay attention to the case of your symbol, whether it's uppercase or lowercase, whether it's capital or lowercase. Look at the symbol for micro. You might not have seen that before. That is the Greek letter mu. It's pronounced mu, MJU. But we just write it like that. It's like a U with an extra little tail on the left-hand side. Okay, so if you haven't got the table down, pause the video, write down all of this table because we will be using it in the calculations just coming up right afterwards. Okay, let's move on. Mnemonic. That was that weird word, mnemonic. It means something that we use to help us remember something. Okay, so in science, a quantity which is written in 1 unit or using 1 unit is often more easily used or understood if we convert it to a different unit. We saw that with the meters and kilometres. Often we will have to convert units with prefixes to base units and vice versa for our calculations. We call this process unit conversion. So for example, converting from meters to kilometres, from kilometres to meters, from micrometers to gigameters, from megabytes to nanobytes. These are all examples of unit conversion. Let's see an example. You could be asked, what could be included in another question, to convert 4 kilometres to metres. Now, if you look at your table, kilo, the prefix kilo, K, same as kilo, is 10 to the 3 or 1,000. So, we can write out 4 kilometres is equal to how many metres? You write in a question mark, write it out like this. If you do it this way for every single conversion you do, until you get very used to it, very good at it, then you don't have to write it out in full. But if you write out like this for now, then you won't go wrong. 4 kilometres is how many metres? We know that kilo is the same as 1,000. If it's written out as an equation like this, with metres on both sides, we can ignore the metres. So just cross out or remove metres. And then we have 4k, 4 kilo, is equal to our number that we want to know, question mark. We know that k is 1,000. K is equal to 1,000. So 4 times 1,000 is equal to the number that we want to know. 4 times 1,000 equals 4,000. So the question mark, 4 kilometres equals how many metres? 4 kilometres equals 4,000 metres. That may be very easy and very straightforward for you, but I think it's worthwhile going over. So that is going from a unit with a prefix to the base unit. You simply use go back to our table, we simply use the meaning column of our table. So kilometre is kilo, is 1,000. So 4 multiplied by 1,000 equals how many metres it is. 4 kilometres is equal to 4,000 metres. Okay. Final check. Have a look at the answer. Does it make sense in your head? Once we've done it a few times, you will start to get a feel for it. I know that there are 1,000 metres in every kilometre. So 4 kilometres is going to be a very large number of metres. 4 kilometres is going to be equal to 4,000 metres. Yes, it does make sense in my head. Okay, just ignore that too easy for now. It shouldn't be there. It'll make sense afterwards. Now, if we go the other way, so for example, from metres to kilometres, we're going from the base unit to a unit with a prefix. You might have a question, convert 54 metres to kilometres. Remember, kilo, the prefix, stands for 10 to the 3 or 1,000. That means the same thing. Therefore, remember, 10 to the 3, 10 raised to the power 3 is 10 times 10 times 10. Do it on a calculator and you'll see it's 1,000. Write it out exactly the same way. 54 metres is equal to how many kilometres? Once again, because we have metres on both sides of our equation, we can ignore them. We can cancel them out. And we get 54 is equal to the number that we want to know times by k. "54 is equal to the number we want to know times by 1,000. If we go to algebra like on maths, if the number we want to know multiplied by 1,000 is equal to 54, then we can find out the number we want to know by dividing both sides of this equation by 1,000. If we divide this on the right hand side by 1,000, we'll have question mark times by 1,000 divided by 1,000. We'll end up with just a question mark. And on the left-hand side, we'll end up with 54 divided by 1,000. So, when moving 1,000 to the left-hand side, we get 54 divided by 1,000 is equal to the number we want to know. 54 divided by 1,000 is equal to, put it into your calculator if you can't do it, or move your decimal place 3 spaces to the right, and you get it as 0.054. So the number that we wanted to know is 0.054. So 54 meters is equal to 0.054 kilometers. There we go. Final check. Does it make sense? I know that a kilometre is much larger than a metre. 1 metre is 1,000th of a kilometre. So does this look right to you? 54 metres is 0.054 kilometres. Yes, it does. It looks correct to me. So I got a good feeling. You'll get feeling about it as you do this, as you practice it. So if that was too easy and you don't want to write out all the steps, if you think that you're getting the hang of it, you can also think of the powers of 10. If we look at kilo equals 10 to the 3, the number that the base 10, that the 10 is raised to, in this case 3, tells you how many decimal places you're going to move when converting between the two. Okay, so 54 meters is equal to how many kilometers? 10 to the 3 tells you you're going to have to move the decimal place 3 places. If you know that 1 meter is equal to 1,000th of a kilometer, you know that the number needs to get smaller. So your decimal place is going to move 3 places to the left. If that doesn't make any sense, don't worry, just do it in the method that I've just outlined on the left. Okay? Okay, here's a bit more of a question. Here's a bit more of a practical example. What is the power in watts when a 12 millivolt LED has a current of 0.2 amps passing through it? We've got the equation up here. Power in watts is equal to current, amps times voltage. So we need to convert our volts. We've got millivolts in our question, but in our equation, we need it to be in volts. Milli, the prefix is the same as 1,000th, 10 to the power minus 3, or 0.001. So the voltage is 12 millivolts, which equals to 12 times by 0.001 volts, which equals 0.012 volts. If you don't know how we got that, then go back to the last slide or the last 2 slides and have a look at that method. I've skipped a few steps there. So then for the power equals current times voltage equals 0.2 times 0.012. There's 0.02 amps. Current times by 0.012 volts is equal to 0.00024 watts. If I hadn't converted the millivolts to volts, this answer would be wrong. Okay, so unit conversions are very important in science. Part B, convert your answer to milliwatts. Okay, we've got 0.0024 watts, and they're asking for it in milliwatts. We do it in the same way as we did the last couple. A milli, the small m, so don't get confused. A small m can mean a meter. A small m with no prefixes does just mean a meter. But a small m in front of another unit means it's a unit prefix and it means it's milli. If you see 2 small m's together, that is a millimeter. So this is a small m in front of another unit, which is the watt. Small m is milli, stands for 10 to the power minus 3, or 1,000th, 0.01. 0.0024 watts is equal to how many milliwatts? Again, just like we did in the other examples, remove the watts because it's on both sides of our equation. We don't need to worry about it. 0.0024 is equal to a number, which we want to know, times by 0.001. Divide both sides by 0.001, and we get 0.0024 divided by 0.001 is equal to the number that we want to know. Work that out, and you'll get the answer as 0.24. So 0.0024 watts is equal to 0.24 milliwatts. If you're very comfortable with this conversion, you'll be able to see it's the same as multiplying by 1,000. We just multiply by 1,000. If you're not comfortable, then do the steps exactly as I've shown, 1, 2, 3, 4, 5, using the table which we've written out. Okay, time for you guys to do some of your own work. If you get stuck, go back through the examples. But I want you to have a go at these. What is 10 centimetres in metres? Remember, there are 100 centimetres in a metre. So 10 centimetres is probably going to be a smaller number in metres. 35 kilometres in metres. There are 1,000 kilometres, 1,000 metres in a kilometre. So this one's probably going to be a larger number. Okay, it's a hinge question, so I'm not going to help you anymore. Pause the video now and see how many you can do. Okay, ready? We're going to have the answers. Don't cheat. If you haven't paused it, then pause it now and have a go. Otherwise, here are your answers. 10 centimetres in metres is 0.1 metres. 35 kilometres is 35,000 metres. 44 gigaamps in amps. Giga, you'll see, is 10 to the power 9. So we move the decimal places 9 places to the right. 44, so that's a million, 44 billion amps. 6 nanovolts in volts, 0.000000 volts. And 305 meganewtons in newtons is 305 million newtons. Okay, if you got 5 out of 5, go for gold. I know it says 4 out of 4, but 5 out of 5, go for gold. If you got 2 to 4, go for silver. If you got 1 right, or you don't really know what's going on, have a go at the bronze ones. Okay, and once you've done one load, you'll see they're quite simple, or you'll see, once you get the hang of it, you'll see it's quite straightforward. See if you can do all of them. Here we go. Bronze, silver, gold, purple. I'd like you to pause the video and have a go at the unit conversions. I'm going to go through the answers right afterwards. This 125 nanometers should be millimeters. If you are converting between multiple steps, so for example, gigaamps to megaamps, I advise you to convert it first to amps and then convert the amps to megaamps in this case. Okay, you can pause the video now. Thank you very much. I hope you're not just letting me talk on and that you did pause it and have a go. You're only sacrificing your own learning if you haven't paused the video and you're just letting it run on. Okay, let's have a look. Let's see what the answers are. You ready? Here we go. 0.06 meters, 33,000 meters, 4 million volts, 0.008 watts, 95, that's 95 billion, is it 95 billion amps, or 95 followed by 9 zeros. 0.078 meters, okay, you can read the rest, okay? Correct your work. I hope you did very well. I hope my explanation was good enough. If it wasn't good enough, I'll put some links in the bottom for places to go to get more help on unit conversions, okay? Okay, that was how to convert between different metric unit prefixes, giga, mega, kilo, nano, etc. Unfortunately, there are some other measurement systems, unit systems, which we have to worry about. The main one is time, okay? Time is not nice and straightforward in powers of 10. As you may have noticed, there aren't 10 seconds in a minute and 10 minutes in an hour. Okay, as it says, sometimes we may need measurements given a non-SI unit, which we have to convert to SI to use. Very common example is time. We might be given a time in hours, and we have to calculate that time in seconds. For this, there are 60 minutes in an hour and 60 seconds in a minute. 1 hour is therefore 60 times 60, 3,600 seconds. So when we're going from 1 hour to seconds, we're going to multiply by 3,600. When we're going the other way, from seconds to hours, we're going to divide by 3,600. It's quite straightforward, really. There we go. 1 hour is 60 times 60, 3,600 seconds. So, hours to seconds multiply by 3,600. 5 hours is 5 times 3,600 is 18,000 seconds. Simple enough. Seconds to hours, divide by 3,600. So 10,800 seconds in hours is equal to 10,800 divided by 3,600, 3 hours. Simple? I hope so. And an example in a physics type question. If this was difficult, if you didn't get this, then pause this and look at it. Give the questions a go. Give the examples a go to try and see it make sense in your head. Okay, so for example, calculate the electrical energy transferred by a 35-watt light bulb when it's on for 4 hours, and they've given us an equation. Energy is equal to power times time. So they asked for the energy, they've given us a power, and they've given us a time. But notice time needs to be in seconds, and they've given it to us in hours. So 1 hour is 3,600 seconds, as we saw. Write out our equation. Energy equals power times time. Energy equals 35, that's 35 watts, multiplied by 4 hours, but we need it in seconds, so we times it by 3,600. 4 times 3,600. Energy is 35 times 4 times 3,600. 35, which we can calculate it out. It's going to be 35 times 14,400. Calculate that out, type it into your calculator, and you'll get the energy, quite a lot of joules, 504,000 joules. Okay. Your turn. Either multiply or divide by 3,600. I'd like you to pause the video and give it a go. You can pause it now. It has been unpaused, I was just joking with you there. Okay, so let's see what you got. 42 hours into seconds. There are 3,600 seconds in every hour. 60 minutes an hour, 60 seconds in a minute. So 42 times by 3,600 is going to be 151,200 seconds. For B, 72,000 seconds into hours. 1 hour is 3,600 seconds. 1 second is 1,3,600. It's 1 over 3,600 hours. It's a small part of an hour. So I divide 72,000 by 3,600 and I get that 72,000 seconds is equal to 20 hours. Okay, we're almost there. Right, we're at the last new bit of information we're going to learn today. Significant figures and standard form. Ignore standard form. We already did that last lesson. Apologies. Just significant figures. Let's say I had some money to give you. I can give you one of these, £1,111, £1,110, £1,111, £1,101, or £1,011. Which, if I was going to give this to you, which amount of money would you rather have? Think about it. If you need to think about it, pause the video and think about it. Which amount would you rather have? Okay, I would rather have, or which one would you least like to have if I was going to give it to you as a gift? Apologies. I would least like to have this one, the £111. So what does this tell us? It tells us that the number to the left, the digit to the furthest left of a number, is the most significant. If I remove this number, if I replace this number with a 0, this digit, with a 0, then I'm removing £1,000. If I replace this digit with a 0, I'm only removing £100. This one, I'm only removing £10, and this digit, I'm only removing £1. So the most significant figure of any number is the figure furthest to the left. And the least important, likewise, is the furthest to the right. If I drop off this figure, this digit of our £1,111, it's the least important. I've only lost £1. We call these significant figures. So significant figures is the number of significant figures is the number of digits that we include. £1,111 to 4 significant figures is the same. These are 4 significant figures. That should be a dot, not a comma. To 2 significant figures, notice we can shorten significant figures to S.F. It's an abbreviation to save us time because we don't have to write it out all the time. To 2 significant figures, that number is £1,100. Okay, so we have rounded up £1,111 up to use the most important, the 2 most significant figures, the 2 furthest to the left. 4 significant figures, 1, 2, 3, 4. 2 significant figures, 1, 2. Why might we do this in science? Sometimes it's useful to restrict why might we care about significant figures. Sometimes it's useful to restrict the amount of detail in a measurement so that it makes it a bit more meaningful to us. For example, if you asked someone how far it was to the centre of town, there we go, there's Hastings here, and they responded it's 3.278 kilometres. They might be very correct, very accurate, very precise, but you'd probably think them quite strange because you're not really asking them for that amount of precision. A more appropriate answer would be to 1 significant figure, which would be 3 kilometres. This could be the same answer to 4 significant figures. To 1 significant figure, it's going to be 3 kilometres. Similar example, if you needed to know how big a chest of drawers was, because you wanted to fit it into a tight corner of a room, the chest of drawers was in someone else's house and they were suggesting giving it to you, for example. They'd advertised it on Gumtree, you'd gone round to go pick it up. Or in fact, you were asking about it before you went to pick it up. You said, how big is it? Because I've got a corner in the room I want to put it between a couple of things. Can you give me its width? And they said it's about 2 meters. This is not very helpful. It's helpful, it's a bit helpful, but let's say my space is 1.9 meters. Then I need more precision than 2 meters. 2 meters, which in this case is 1 significant figure. It's one digit from the leftmost digit. Is not enough detail, not enough precision. 2.46 meters, that's 3 significant figures. So going from the left, 1, 2, 3, or I might even convert it to centimeters. This would still be to 3 significant figures, 1, 2, 3. Is going to be more appropriate in this case to give me a better idea as to whether the chest of drawers are going to fit in my gap. Okay, so the rounding of a number to the level of importance in the details that is most useful is known as using significant figures. The number of significant figures used is equal to the number of digits that are kept as important during the rounding of the number. That's quite confusing. So let's see it as an example. The average distance from the Sun to Pluto, so Pluto is the dwarf planet, which used to be a planet when I was small, but it's recently been knocked down to a dwarf planet. They don't call it a planet anymore. The average distance from the Sun to Pluto is 587040000000 meters to 5 significant figures. You can tell it's 5 significant figures because going from the leftmost, it's 1, 2, 3, 4, 5. Every other number is rounded to 0. They're still important, you still have to include them, but they are 0. And what is here, which we can't see, but it is there, is a decimal place, which indicates where the unit columns are, where the unit column is. So, this average distance, in fact, Pluto, as we saw last lesson, has a very highly elliptical orbit. It's also very eccentric. So, giving the answer to that amount of precision, that amount of significant figures, might not be appropriate at all. They might want to give it to 2 significant figures. If we're asked to give it to 2 significant figures, we're only going to need to include the first 2 digits going from the left. So you might think 58000000, but in fact, because this is 587, the next digit to the right is 5 or above. It means we're going to round this one up to 5590000. There we go. 59000000. That is rounding is the reason why we go up to 9. If you're not sure about rounding, I'll include a link on the bottom of the video, but you should have done rounding in maths. Now, some astronomers might even think, do you know what, that's too accurate itself, or that's too precise. Because in fact it varies so much. They might even want it to 1 significant figure. If we're going to go to 1 significant figure, 59000000, we're only going to include this one on the left. The one immediately to the right of it, the digit immediately to the right of it, is above, it's 5 or above, so it's going to round up to 1 significant figure. This is going to be 6 trillion meters, or 6 terameters. Tera is the one above gigameters. It's times 10 to the 12, 10 to the power 12 meters. Don't worry too much about that. There's a T. Okay, your turn. So, what is the furthest distance from the Sun to Pluto to 3 significant figures? The NASA website says the distance is this. That is to 5 significant figures. I want you to reduce it to 3 significant figures. Pause the video and give it a go. Pause the video now. Thank you very much. Hopefully you've given it a go. The answer is 732,000,000,000,000,000,000,000,000 meters. Note, again, because the number to the right, so we've got how many digits from the left? We've got 1, 2, 3 digits from the left, which we include. Everything else goes to 0. Notice that the 1 has been rounded up to a 2 because the number to the right of it is 5 or above. All the rest go to 0. Oh, we're there. We're almost at the end. So we are at the end. We're at the exit ticket. Before we go on to the exit ticket, just want to say how you will see significant figures most commonly is on the GCSE paper or on your papers. It will say, it'll give you a question and it will say, can you calculate this? Give your answer to 2 significant figures. They might also just write S.F. or give it to 3 significant figures. If in doubt, a fairly good rule of thumb is to give it to 3 significant figures on GCSE answers, but they will tell you what precision, what significant figures they want you to use. Okay, here's our exit ticket. We've got 3 questions and we have 4 questions and a 5th one on the next slide, okay? So we had so many, I couldn't fit them all onto one slide. Number 1, list the unit prefixes that we need to know for GCSE Physics. And they're going to help you out an awful lot for biology and chemistry too. And also in just general life. So, Giga, for example, Giga and Kilo. List the unit prefixes, and if you could do it in order, please, from largest to smallest. The largest you need to know is Giga. That's the clue I'm going to give you. Number 2, I'd like you to invent your own mnemonic for remembering the multiples in order. The multiples, I mean unit prefixes or multiples, okay? So a mnemonic for remembering giga, mega, kilo, and so on. You can go back to the slide with the table of all of the unit prefixes on them, and you can see my mnemonic, but I'd like you to come up with your own mnemonic for remembering the order. It's going to begin with giga, so a word for G, word beginning with G. Number 3, sorry, it's covered up by this box, but number 3, convert the following units, giving your answers to 2 significant figures. So convert 2 kilometres to meters, 320 meters to kilometres, 0.0458 grams to milligrams, 6,258 meganewtons to newtons. Number 4, convert the following units, giving your answer to 2 significant figures. See, I've started to put in some standard form here as well. So again, if you haven't done standard form from last lesson, then you need to go back and do the online lesson from last week. 6.4 times 10 to the 6 meters to megameters. That was our radius of the Earth. B, 3.284 times 10 to the 8 watts to gigawatts. C, 0.0004003 joules to microjoules. And D, 10,000 years to seconds. And finally, number 5. Here we go. The Earth has a radius. This one's a bit more involved, but don't be scared. We will get through it. I will show you how. It's not actually too hard, okay? The Earth has a radius, that is the distance from the surface to the centre, of 6.371 times 10 to the 3 kilometres. If there was a hole from the, sorry, that's not written correctly. If there was a hole from the surface to the centre of the Earth, and I were able to walk down it at a speed of 1.5 meters per second, that's the average human walking speed, how long would it take me to get to the centre of the Earth? Give your answer in seconds, in standard form, to 3 significant figures. And extension, if you like, if you've done that, then have a go giving your answer in decimal hours. Now again, how do we go about doing that? It's step by step. Okay, convert. I'm giving you so many clues here. Number 1, convert the radius from standard form to a normal number. So to convert 6.371 times 10 to the 3 to a normal number, from standard form to a number of kilometres. Then convert it from kilometres to meters. Okay? So first of all, convert it from standard form to a normal number, then convert it from kilometres to meters. Then use time is equal to distance, time in seconds is equal to distance in meters divided by meters by speed in meters per second to calculate the time it would take. You should have the distance in meters. You've calculated it. You've been given the speed in meters per second, so just divide the two. Finally, when you have your speed, your time, when you have the time, you'll just have it in seconds if you've got the numbers right. Convert it to standard form. So it'll be a number between 1 and 10 multiplied by a power of 10. And make sure that your answer only has 3 significant figures. Okay, good luck. I wish you all the best of luck with that. Honestly, if you just go through the steps step by step, you should be able to do it. It shouldn't be too bad. If you have any problems with any of the things that we've done today, I'm going to include links to the bite-size topics below the YouTube video. Okay, so unit prefixes, converting between units, standard form, converting from hours, etc. Okay, so look below the YouTube video and you'll see the links to help you. Okay, thank you very much. If you've made it to the end, thank you very much for your attention. I look forward immensely to seeing you next week and hopefully seeing you back in school before too long. Who knows when? Certainly not us. Goodbye.